Okay, so I'd like everybody to kind of come back, and what I would like to do is find out, do you guys need more time to whiteboard, or can we do at least some of the presentations? I understand some people are joining the game a little late. Don't want to mention any names, Philip.
Sorry.
That's right. Sleeping in. But some people, I'm hoping, maybe can whiteboard, and maybe we can get a consensus from that, and maybe even work out some of the problems on that lab sheet. So is there anybody that would be able to share the whiteboards?
I think we did our graphs.
Okay. Let's see if I can share it with you. Reagan, that was you, right?
Mm-hmm. Yeah.
I'm going to see if I can swap it to you, and so we can see what you've got. Okay, so it looks to me, correct me if I'm wrong, but it looks to me like you found between acceleration and the net force, it looks like a, is it either linear or is it a direct relationship?
I think it's just linear.
Okay, so was there a y-intercept or not?
No. Actually,
Oh.
no, it might be direct.
So it is actually a direct relationship. Okay,
Yeah.
cool. And then for the acceleration versus mass, you found an inverse relationship. And it looks like you linearized that. And did the y-intercept drop off then after you linearized?
Yeah, I think so.
Now,
0.0008.
Okay, now I do. Okay, I do have a question though. In that equation right below the acceleration versus mass, wouldn't that be acceleration equals 20 times 1 over m?
Yeah.
Okay. What would the units be for that, by the way? 20 what?
Meters per second squared times mass.
Which is kilograms. Kilograms.
Yeah.
Cool. Thank you very much. So it looks like we have a direct relationship and an inverse relationship for mass. Okay, can we have, I'm going to take the presenter role back. Thank you, Reagan. And let's see. Can we have another volunteer? Because again, we're trying to get consensus.
I guess I could.
Who's that?
Hassan.
Hassan, let me see if I can switch it to you. Where are you at? There you are. Okay. Okay, very nice. Okay, so the acceleration and the force, you got, looks like another linear relationship.
Yep.
And
Yep,
is
that's
the,
inverse.
oh, okay, so, okay. So you also got a linear relationship and an inverse relationship.
Yeah.
Okay. What was the, I'm just kind of curious for when you linearize the inverse relationship.
Yeah.
So is it acceleration equals 0.0396 whatever units that'd be times 1 over m?
It would be. Actually, don't. It'd be kilograms times seconds squared over meters, right? I think.
Well, I think it's going to be kilograms because it's going to be, because this is acceleration on this axis, so it's going to be meters per second squared divided by 1 over kilograms. So the kilograms, you're right, comes up in the numerator.
Yeah.
Okay, so you are agreeing with Reagan a second ago. I'm going to go ahead and take the presenter role back. Okay, so do we have any others you could share? Again, the whole purpose here is to get consensus. I'm getting some echo, so if you guys can please make sure you have your headphones on. Okay. Or maybe you can kind of mute your end or something. Is there anybody else can present?
I can present.
Who's that?
Ben,
Ben, let's see here. Okay.
is my volume?
Yeah, your volume's fine. Okay. Ben?
Can y'all hear me?
Yep.
All right, sweet. So I basically got the same thing as the other two, direct relationship for force versus acceleration, and then indirect for mass versus acceleration.
Okay. Now, and I'm a little curious, for that second, where you had to linearize the inverse relationship, what was your constant force?
It was 30 newtons.
Notice the slope there is 30. That's kind of interesting.
Mm-hmm.
Okay, let's see if we can get one more. It looks to me like we have a nice consensus already, but I'd like to get one more. I'm going to take the presenter role.
I can go.
Okay, that's Michael, right?
Yeah.
Let's see, all right. What's going on? Mike, I'm going to skip you for a second because, wait a second. Michael Bart, you said that you were going to present, didn't you?
Yes.
Okay, and then after that I'll have Mike Smith present. Okay, Michael, okay. Okay, so tell us what you found, Michael.
Okay, for the first one with a mass of 1 kilogram, I got it's a direct relation, basically
Gotcha.
a slope of 1. And then the other one was an inverse, just like the others, with the slope being 19, which is kind of close to what the force was for the
Okay.
constant.
All right, so you're agreeing with all the other groups so far.
Yes.
Okay, I'm gonna I'm gonna take the presenter role, and I'm going to pass it over to Mike Smith. Let's see right here. Yes. Okay, Mike, it's all yours.
Okay, can you guys hear me?
Yep.
All right, so this is our relationship for mass at the top. I guess we put them in opposite order.
That's
But
all right.
Here it is. We had about 50 kilograms times meters over seconds squared times 1 over m for the mass relationship. And that was for a 50 Newton force. So it would appear that the acceleration equals force divided by mass.
Okay.
And I guess this is just our linearized version. We don't have the first graph in there. But my model on my paper was that it was pretty much the same general model, A equals F over M, except the number in the equation was the 1 over M, and then force was the variable instead of the other way around.
Okay. So it sounds to me you're saying for the acceleration versus FNet, you found a linear model just like the other groups.
Yeah, we've been
Okay.
finding the same thing.
Okay, I'm going to go ahead and take a presenter role. And I'll kind of get a synthesis, consensus here on what we found. And so this is what we found. I'm gonna, because I'm getting a lot of echoes here, I'm going to turn this on to a just present. If you guys have questions, please type it into the little chat, and I'll see if I can keep up with it. Okay, for the acceleration versus FNet, what you guys said was that you found a relationship like this. Okay, now make sure you put in your point protectors and your slope indicators and everything. One thing I would critique on it, it looks like some of you guys have kind of forgot how to title the graph here. It's going to be acceleration versus FNet. Okay, then for the other one, we found kind of a inverse relationship like this. So this had to be linearized. And for this one, this would be acceleration versus 1 over m. And you should get a nice linear relationship like this. Okay. And again, make sure you title this appropriately. Okay. So from this, our relationship that we found over here was that A was proportional to, and I don't have a proportionality symbol, so I'm just going to say equals some constant times FNet. And if you look very closely at the units here, the units of that constant were meters per second squared per Newton. And from this relationship over here, we found the acceleration equals some other constant. And the units were meters per second squared per 1 over kilogram. That puts the kilograms up in the numerator. So actually, I think I'll write it like this: kilograms times meters per second squared. And then this was times 1 over m. Now we should be able to combine both of these models together into one model. In other words, let's get one joint consensus model here. And that's going to be acceleration equals some new constant. I don't know what I'm going to call it here. Let's call it z times FNet over m. And the reason for it is that this constant here, this big K constant, must be equal to some z times FNet. Okay. So let's see, I'm kind of running out of room here. In other words, the big K constant must be equal to z times FNet. Well, you know what your FNet was for this second experiment. So that means you should be able to figure out what z is. So z equals question mark, and you should go ahead and calculate that for yourself. We can do the exact same thing for figuring out what the little c constant is. So in other words, the big K constant must be equal to the little c constant. Wait a second. I did it wrong, sorry. The little c constant must be equal to big Z times, let's see, that's going to be times 1 over m. And you knew what your mass was in that first part of the experiment, so you should be able to figure out what Z is. The point is that Z should be the same for either experiment. And we already had some groups go ahead and do that. Could somebody type in what is Z going to be equal to? What is Z? So this is the experiment. This is what we have. Here's our consensus model, but we need to figure out what the Z is equal to. No, I don't think it's Z is equal to F. It's some kind of numerical constant. Two. Okay, so one group we have 2. So if that is the answer that everybody comes up with, oh, that's not me. Oh, okay. Well, I'm going to go ahead and go with that, Luke, for a second. Let's just say that was it. You're backing off of that now. Then what you're saying is that A equals 2 times F net divided by M. Hassan gives us a half. Kurt says 1. Oh, Luke randomly picked a number. Okay. So we have 1/2 and we have 1 so far. We need some other ones because we still don't know what the consensus model is. We know it's A equals something times F net over M. Three doesn't, I mean, it sounds to me like we're guessing here, guys. I think we're going to have to call it quits because we're not getting answers. Okay, so let's see, I need to do some erasing here. Okay, I'm going to go ahead and turn it back on so you guys can talk. Okay, Andrew, you said you weren't able to figure out what's going on here.
Yeah.
So right now, our consensus model, A equals Z times F net divided by M, but we need to figure out what that proportionality Z is equal to. So for the first lab that you did, what was your mathematical model here so I can type it down? A equals...
For the F net or the...
Yes, the F net one. Yep.
It was 1/2.
So you had 0.5 meters per second squared divided by newtons times F net, right?
Yes.
And by the way, what was your mass? M equals what?
2 kilograms.
2 kilograms. Okay, so if we're looking at this, we have that Z is going to be equal to, let's see, it's going to be equal to 0.5 meters per second squared times 1 over the mass. Well, if I plug in 2 kilograms here, 2 kilograms, oh, and I forgot my units here, I forgot newtons. per Newton. If I were to take 0.5 times 1/2, wait a second here. Oh, wait a second. Something not working here. Oh, sorry, not times 1/2, times 2. I'm sorry, times the mass. Because we're trying to figure out what that is. Sorry. Times the mass, which would be 2 kilograms. What is Z going to be equal to? It's 1, right? So Z's 1. Z's equal to 1. Okay, now let's do the second part of the experiment. What'd you get for that, Andrew? What'd you get? A equals what?
10.
10, and that was kilograms times meters per second squared, and then that was times 1 over m. And by the way, what was your F net?
10.
10. Okay, so it's 10 newtons. Now somehow that F net is somehow in here in this, and so let's see what that would be. It would be Z equals 10. Boy, I'm getting some major feedback. Times meters per second squared. And then I have to divide out the that 10 newtons you found. So what do you get Z for this one? Z is also 1, right?
Mm-hmm.
Okay, so that works out. So our consensus model is actually just A equals F net over M. So that's our consensus model.
All right.
Okay, I didn't get quite as far as I wanted to do. I wanted to actually look at some of the problems on the back side. So I'd like you to go ahead and do that for homework then tonight. And that's it. We didn't have enough time to do any more. Any questions before you go? No. Okay, thank you for coming. See you guys tomorrow, hopefully. Bye.